Yes, thank you for the introduction. Welcome to my talk. I will explain to you how you can find out how sensitive your application is to changes in memory latency. And the motivation why you might be interested in such a question is because it is becoming more and more popular to disaggregate resources. So instead of having many nodes that are all the same and you access your local memory over, let's say, your motherboard, you might be interested in transitioning to a model where you have dedicated nodes with a lot of RAM and thus accessing memory over some network fabric. And what also plays into that is that the network fabric is becoming more and more is getting more and more bandwidth. However, this higher bandwidth comes at a cost. The cost is that these high bandwidth networks require more complex forward error correction algorithms to be applied to be reliable, and thus you increase latency. So if you want to go that route, it would be very interesting to know what will happen to my application. Right? And maybe not only to your whole application, but maybe you even want to rank certain kernels in your application, and you might want to say, okay, this kernel in my application really doesn't care about the memory latency because all the memory accesses are overlapped with some computation, and some other part of my application does not do this overlapping at all. So it will be very, very sensitive to especially increases in memory latency. And so how would you find that out? How would you do that? And the classical way to do this is you can, of course, say, well, you just build a system like this, right? So you do hardware modification, either by running on an actual system with higher latency or kind of changing maybe your DRAM controller to add latency. But as a software guy, that sounds difficult, right? That's kind of difficult to build such a machine. It's also inflexible, so once you changed your DRAM controller, you can't probably switch it back just to run the next kernel. And the next option you have is simulation. So you take something like Gem5, which is a cycle-accurate simulator for many different processor chips, and you run your application within that, but you will quickly notice that running something in such a cycle-accurate simulator is very, very time-consuming. How time-consuming? We actually check that. So in this plot, you have runtime on the y-axis and different PolyBench kernels on the x-axis. And if we run these kernels on some RISC-V SoC. I forgot which one exactly, but that is in the paper. Doesn't also really matter for this presentation. You can imagine some small SoC like a Raspberry Pi level system. And then you run the same thing on Gem5, and you get a runtime increase of, what is the biggest here? 600x. So it takes 600 times longer to run this application or this kernel in simulation in Gem5 than it did on the real system. So that's not so great. But instead, with our tool that I will now present with EDAN, we can get the same information, like this latency sensitivity information out with only about a factor of 10 of slowdown compared to the actual run. So how do we do that? Our toolchain looks, from a high level, looks like this. We take our input program, we compile it to a RISC-V binary. RISC-V is completely arbitrary here. We just want something where the assembly is easy to parse. You will see why later, but you could use any other ISA here. You just need to parse its assembly, and if you use x86, you will have a lot of fun learning about all the different addressing modes and so on. So something like RISC-V is easier. Then you run this RISC-V binary and you trace the execution. So you want kind of a trace of which assembly instructions have been executed, and this you feed into our execution DAG generator. So you take your trace and you transform this trace into a graph. We will see what kind of graph later, and then you can perform analysis on this graph. So this is the red part. And what you hope to get out is some sort of performance metric. And I will describe each of these boxes in detail in the following. So first, let's see what are these EDAGs. So on the top here, we have some very simple code. We define 3 variables and calculate their sum. And you could express this as an execution DAG that is shown below, where each vertex is one assembly instruction, and the edges between these assembly instructions are data dependencies. So maybe you are not familiar with RISC assembly, but basically the only 2 instructions that are shown here is LI, which is load immediate. So we are loading some value into a register. The registers are named A1 to A5 in this example. And then here you can see once we loaded 1 and 2 into 2 registers, we can use the add instruction to sum them together, and we store the result in another register, and then we use another add instruction to basically do our second addition. And we can express this nicely as a graph. So why are these graphs useful? Because there is some theory on how to analyze them, right? So if we define these vertices and edges, we can define the total work of our program, which is basically the sum of the work of all the vertices. And we can define the parallelism of our program, or the average parallelism, by dividing the work by the longest path in this graph. Because the longest path, of course, has to be traversed somehow, and because this path is formed by data dependencies, you can't execute your program any faster than traversing this path. So this longest path limits your, or it's also called depth, the length of this longest path limits your parallelism that you can obtain, or how fast you could execute this graph with an infinite number of processors. And so you can bound your execution time on the left side by saying, well, I can't be faster than dividing the sequential program perfectly among my P processors, and I also can't be faster than this longest path, so the time it would take for an infinite amount of processors. And there is also Brent's lemma, which gives you an upper bound by basically assuming that you are using a greedy scheduler, and then you are forming different levels. I don't want to go into deriving Brent's lemma here. Everybody that has studied computer science should have heard this at some point, and we will just kind of use this formula later when we want to go to memory latency sensitivity. Okay, so this is kind of the basics. So let's look at this pipeline in a bit more detail. So we take the input program that can be C code, C++ code. It is really kind of agnostic. The only thing that we need is we need some compiler. In this work, we use GCC 12.2, and we optimized with 03 to get a RISC-V binary out of it. Again, RISC-V here is not important. We just need something that we can both execute. So for execution, we used QEMU in this work. And we added a tiny plugin to QEMU to basically give us a trace of all the instructions executed. And we could change to other ISAs. RISC-V here was a relatively arbitrary choice. And then we take this instruction trace that looks like this. So we have all the assembly instructions and the memory addresses as well, right? So that is important. We don't want to get into static analysis and alias analysis. So we really want to say, for this execution, which memory address was accessed. And then we take this trace and we generate an EDAG out of it. The EDAGs we have just seen how they look for this simple sum. We also need a cache model because we need to decide which accesses in our trace actually go to the cache, because then that means they are not sensitive to memory latency, which accesses actually go to memory. So here you can see we have drawn such an EDAG, and all the nodes or all the accesses that go to memory are colored in red. And which ones they are, this of course depends on your cache model. Okay, so first of all, how does this help exposing parallelism? So here we have some assembly instructions, and you can now see, we now have the task to basically, these assembly instructions we get from the trace, we now have the task to form edges, right? To say, well, which instruction depends on one another. And how we do this, we look at the operands of these instructions. So here we can see we have a load that stores something in A1, and we have also a load that stores something in A3, and we have a multiplication that reads from A3. So we can say that whenever an instruction reads or writes the same value as something else, we draw an arrow between them. And if we do that, some of these dependencies are what we call true dependencies, so read after write dependencies, where we really need to wait for some assembly instruction to finish so that the next one can read its output. But if we continue like this, we will also see we have some sort of false dependencies. So for example, okay, first if we continue with these false dependencies included, we will see that the depth is 6 here, which would give us an average parallelism of only 1.67. But if we are more careful with how we draw our edges, so you can already see we are careful because we drew some of these edges with dashed lines, you see that some of these dependencies are actually read after read dependencies, right? So in this example on the bottom right, we store something in the register A5 only to overwrite it. Is it like this? No, we read something from A5 only to read the same value later again. So here we would say, well, just because I read something twice, this is not a true dependency. So you have to be a little bit careful when you form these edges to only take read after write dependencies into account and not these false dependencies. There is another source in this kind of analysis we will see at the end. There is another source of kind of falsely introduced dependencies based on your compiler and how many registers it thinks it can use. But this type of false dependencies we actually eliminate. So if you use our tool, it will remove those and it will actually give you this graph. And here we see the depth is now 5 and it gives us an average parallelism of 2. Okay, that's nice. How about the memory cost model? How does that work? So if we have a simple summation kernel, we get the following graph. And what we are now interested in is how does actually our memory subsystem affect the performance of the execution? So what we are essentially interested in is how many memory operations lie on longest paths through this EDAG. And to do this, we need a couple of parameters. We need to say how much cycles do we need to do a memory access, and how many memory accesses can we issue in parallel. So this is kind of machine parameters that we can vary. And then we can define, just as we defined depth and work before when we discussed Brent's lemma, we can basically define the memory work and the memory depth, right? So this is very similar to what we did before. It's just now we only consider memory operations, and we are interested in how many of those could be issued in parallel. So then we can apply the same bounds that we've seen before. So we can now say, depending not on P, which before was the number of processors, but depending on the number of parallel issue slots basically we have, we can execute this sort of memory work faster, depending on how the graph looks like. So maybe some loads are not parallelizable if they depend on each other. Then it doesn't help me if I have a lot of parallel issue slots, but I'm doing pointer chasing. But if I'm doing a lot of parallel loads, then having a lot of issue slots would help me. So we use exactly the same bounds that we introduced before. Just now we have different notation because we are concerning only loads and stores. Okay, that is nice. And now what is this sensitivity analysis? So what we can now do, we can take these bounds and we can take the first derivative of that. And now we get an expression that basically parameterized by this m and by this m parameter, by how many parallel issue slots do we have in our system, how sensitive is my runtime of my application to changes in other parameters, like to changes in this alpha parameter, that is the RAM access latency. So this is what we can do in our analysis. And you see here two examples. So there is one example of a very memory latency sensitive application. That would be an application where we have 3 loads that hit the memory and not the cache, and they all depend on each other. So for this, even if we have 3 parallel memory issue slots, we would get a memory latency sensitivity factor lambda of 3, because yes, this is very sensitive because we 3 times incur this higher latency, and the opposite would be a very latency insensitive application where if we have our m equals to 3, so our 3 parallel issue slots, even though the work is the same in this case, or the memory work, we have 3 access to memory, the depth is lower, and thus our lambda would be 1. So it would be a very latency insensitive kernel or application. So how do we validate that this actually works, right? So it's nice to have this theory based on Brent's lemma, but we somehow need to check if this actually works in practice. So what we did, we varied the DRAM access latency for all memory accesses in Gem 5, and we ran all the PolyBench kernels for many different memory access latencies. So basically on the x-axis we show the memory access latency in nanoseconds, and the execution time of the kernel is shown on the y-axis. And then you see for many different kernels, you get these sort of lines, right? So first of all, that's kind of surprising that this is a line. There could be some steps there. You see for some kernels there are actually steps, but they are tiny, so you could approximate all of these as lines. The important takeaway here is that this simulation took a lot of time, because you need to do this simulation for each point that is in this that is drawn in this plot. And now we can rank how sensitive an application is to this latency increase, basically by ranking them by the steepness of this line, right? So if the line is flat, that means even if we increase the latency, the application runtime didn't change. If the line is very steep, then that means the application is very sensitive. And this steepness is exactly our lambda parameter. So here we also annotated which kernels they are. And we can see that in EDAN, this analysis took only 1 hour. In Gem 5, this took about 24 hours. So now we did the same thing. We now plot it differently. We now sort them by steepness. And we sort them by steepness based on the Gem 5 output that you just saw and on the EDAN lambda parameter. And you see that we are not perfect. So basically, our largest error is we are off by 2. But for most benchmarks, we are very close. So we are either ranking it exactly or very close. And I think that is an impressive result if you consider how close some of these lines were next to each other, right? And we did that in 1 hour compared to 24 hours. So the maximum difference is 2, I said that. So what can we see from there if we do this to PolyBench? One interesting thing is that you would think that all of these PolyBench kernels, they are actually data oblivious, right? So they shouldn't need any sort of pointer chasing, but still some of these kernels exhibit very high memory latency sensitivity, and others did not. So why is that? All these data oblivious applications should have constant memory depth. Well, the reason is register spilling, and this is kind of the second source of these maybe not fully true dependencies, right? If you would look at this kernel, you would say this should have constant memory depth, but what actually happens that between these accesses of these different values of B, you are accessing so many variables that they just don't fit into registers, and it causes register spilling. And then it looks to the analysis, yeah, you actually wrote to memory and read from it, so now you are memory latency sensitive. So unfortunately, the compiler also plays a role here. Your compiler, if it does bad decisions or bad kind of tiling in your implementation, you can take a application that could be implemented perfectly memory latency agnostically, and you get something that's memory latency sensitive. But kind of fixing that was outside of the scope of this work. So, and in a sense, that is also true. If you would compile that and run it, it would be memory latency sensitive, right? It's just something to be aware of. Okay, another thing that we did is what about the effect of the cache size? So here we took the HPCG benchmark and we ran memory latency sensitivity analysis for different cache sizes, so either no cache or a 32 kilobyte cache or a 64 kilobyte cache, and we can see that for the HPCG code at least, this didn't have a big impact on memory latency sensitivity, which was interesting. It could be that if we increase the cache size a lot more, then this would look different. But this is another example for what EDAN can do. And with that, let me conclude. So I presented you the EDAN toolchain, and I showed you that it's almost as exact as Gem 5 in doing this ranking of memory latency sensitivity and how it does it. And I showed you some examples of what you can do with that information. And of course, if you want to use this toolchain, this is fully open source, and you can download it from GitHub, and we hope you do so. Thank you.